Dear Sir, Madam, and everyone, I am Ngọc Nguyễn from Vietnam. Today I am very honored and happy to present my research, the global optimization with descending region algorithm. This research was presented at the Turk Science and Technology Conference of Ho Chi Minh City University of Food and Industry in July 4, 2017, Ho Chi Minh City, Vietnam. The descending version DR algorithm, the global optimization, is general form of local optimization. A follow mean Fs S belong to S over S upon S star equal the global optimizer if Fs is larger than or equal to Fs star for on S belong to S. Because the cost of finding out S star is very expensive. The approximation approach accepts a small error in which the global optimizer S star is replaced by a so-called global epsilon optimizer omega such that S F S is larger than or equal to F omega subtract epsilon for on S belong to S. The descending region DR algorithm is a practical implementation of approximation approach. I use the very small the I use the very small value epsilon as a downward shift to determine the feasible, and I use the region descent GD method to search for local optimizer, which is the candidate of the global epsilon optimizer. I speak again. The descending region DR algorithm is a practical implementation of approximation approach. I use the very small value epsilon as downward shift to determine the feasible bond, and I use the region descent GD method to search for local optimizer, which is candidate of the global epsilon optimizer. The ideology of the algorithm is that given a known local optimizer G star, the better local optimizer is searched only in a so-called descending region under the node bound G star. If the target function has the global minimum value, the local optimizer G star approaches the global optimizer G double star. The descending region is begun by a so-called descending bond, which is defined as the bond under the optimizer G star, and so the next better optimizer is searched under descending bond. Descending bond is the solution of a so-called intersection equation mentioned later. The algorithm has many iterations, and each iteration includes two steps. Step 1. Searching for the local optimizer G star by GD method. Step 2. Determining descending region, descending bond. This track shows the descending region DR algorithm. You see that? This is the descending region. There are two descending region. Descend region. Two descend region. How to determine descending region? Descending region is determined by descending bond, which in turn is the solution of the intersection equation Fs subtract S star at epsilon equals 0, where S star equal Fg star, and G star is a local optimizer, whereas epsilon is a very small error. Following equation is the hyperline which represent the intersection between tangent hyperlength and hyperlength is y equal to equal 0. I speak again. Following equation is the hyperline which represent the intersection between the tangent hyperlength and the hyperlength y equals 0. And so it's equal the intersection hyperline delta f s0 s subtract c0 equals 0, where c0 equal delta radian. The delta notation denote the radian. Radian f s0 s0 s f star subtract f s0 subtract epsilon. This equation has many solutions which are both belonging to it. Now we find out only one solution, S1, such that S1 satisfies two following conditions. Both S1 is the projection of S0 on the intersection hyperline. Bond S1 belongs to the intersection hyperline. How to determine the descending region? Continue. I prove that S1 is the solution of the following system of linear equation: A0 S1 L equal B0, where A0 here. You can see that they are the partial derivative. B0 S0 C0 0 is the C0 is the region. F S0 region. 0 is the region. F S0 S0 S F star subtract F S0 subtract epsilon. I propose the iterative method, which is a simulation of the Newton-Raphson method, so as to solve such equation. The proposed method is called simulated Newton-Raphson SNR algorithm. Suppose we have an approximated solution Sk at the kth iteration. We set up such equation based on Sk in order to find out the net better solution. Sk is not 1. How to choose the optimal starting point? The volume is defined as the subspace denoted V AB or the interval AB. Solution volume is defined as the volume in which the descending point is existent according to Bonzeno-Cauchy theorem as follows. The interval AB solution volume equivalent to their acid vector S vector Y belong to the interval AB such that the product Fs Fy smaller than or equal to 0. The problem needs to solve is to select the starting point S0 so that such point is in the solution volume where SNR algorithm converges. The optimal volume is the one that satisfies the following condition. is in the interval AB. In other words, AI, the interval AI, BI belong to the interval AB. The interval AI, BI is contained in the interval AB. It is also the solution volume satisfying Boseno-Cauchy theorem. It is a small a possible. This condition have SNR algorithm to converge a fast a possible. I propose a so-called random test bond RTP algorithm to find out the optimal volume. Firstly, suppose S and Y are bound in the interval in the volume AI BI such that Fs larger than 0 and Fy smaller than 0 respectively. Hence, S and Y are called positive bond and negative bond respectively. Let n positive I and n negative I be the number of positive and negative bonds respectively, and let Bi be the ratio of n negative I to the number of total bonds. Ni in the optimal volume AI Bi A follow Bi equal n negative I divided by the sum and positive I at n negative I equal to the ratio n negative I divided by ni. RTP algorithm is based on the two heuristic assumptions. If AI BI is the optimal volume, then the probability BI larger than 0 and smaller than 1. In other words, both n positive I larger than 0 and n negative I larger than 0. The nearer to the half of the probability Bi is, the more likely is it that AI Bi is the optimal volume. How to do the optimal starting point? RTP algorithm has finally many iterations. We do two tasks at each iteration. 1. Creating many enough random bonds in each volume AI-BI. 2. Counting the number of positive and negative bonds and positive I and n negative I, and calculating the probability BI of each subvolume AI-BI based on the n positive I and n negative I. Which subvolume that has the probability Bi being larger than 0 and smaller than 1 and nearest to the to nearest to the half is chosen to be the input for the next iteration. There are two stop conditions for RTP algorithm. 1. The first stop condition. The deviation between the probability Bi and the half 1/2 or the capacity C AI-BI is smaller than a small redefined number than R, or the algorithm reaches the maximum number of iterations. Conclusion. The action of the algorithm is to solve the linear system equation many enough times with aims to solve the intersection equation. In other words, the Hazard problem of the global optimization is in fact the most common problem, with not that linear equation is always solvable. In general, I combine three algorithms such as DR, SNR, and RTP to solve the Hazard problem of the global optimization, in which DR is the backbone to connect itself with SNR and RTP. DR algorithm DR algorithm will improve significantly if we can predict that the intersection equation has no solution before solving it, or we can predict the solution volume. In the future, I will research deeply how to approximate such equations into similar forms such as exponent, function, and polynomial in order to apply easily prediction tool. I suggest a so-called segmentation approach for solution prediction, in which the solution volume is split into many small enough segments. Later on, for each segment, approximation methods such as feasible length and minimizing square error are applied to approximate intersection equation by Taylor polynomial intersegment so that it is accurate to predict solution volume of such polynomial. Final solution volume of intersection equation is the best one for many polynomial over all segments. This approach shares the same ideology of volume partitioning with RTP algorithm. It can be more complicated. It can be, it can be more complicated, but better than RTP. Thank you for your attention. I am very honored and happy to answer your question. There are references. Thank you again.